This is 3, 4 alpha. And on page 127, you have this. It's the difference quotient. You need to make sense of this, okay? You look in your book on page 127, and I'm going to go here, and you have to say, oh, yeah, sure, that makes sense. I knew that. That is going with this. You have a T-chart. You have X and Y. And we're really going to expand it to an H chart, and we're going to put dy, dx out here. But for now, you have to make a connection between X and the output being f of X, whatever the function does to X to give you the height, X plus H, f of X plus H. And what's on page 127 is subtracting up. This take away this, over that take away that, which would give you the slope. And what? The slope, ready, in the denominator, X plus H take away X, the X is subtracted to 0. So the numerator is the difference of the dependent values. But then when you put this in here, the limit as H goes to 0, then this gives you the instantaneous slope, which is the derivative, which will be the value we put in the third column of the H chart. So, a little carried away there. Example 1. It's enlarging circles. Find the rate of change of the area of a circle with respect to its radius. Evaluate that, the two places, and units. So I'm going over here. Ready? The area of a circle is pi r squared. The derivative, the change in area with respect to the input, which is radius, is the power rule. Pi is a constant. It would just be pi times 2r, or 2 pi r, commutative property of multiplication, it doesn't matter. So here's my H chart. I've got my input, my output, and my instantaneous change. So as per the example, if I put a 5, if r is 5, the area would be pi times 5 squared. The instantaneous change would be 2 times pi times 5. If I put 10, I would get these outputs. So what's happening? The area is expanding faster when the radius is larger. And units. Ready? Now you can just think through this. The derivative, the change in A with respect to R, area is in square units and radius is in linear units. Now, if we have the old school AP test, which we had up till 2019, then FRQs, of which you'll get 6 of them, are arbitrarily, I mean, it's worth 9 points each, but every FRQ, and your goal, don't worry about 9 points, you're trying to get 6. If you could get 6 out of the 9 points, you'd be on pace to get a 5. But if you omit units in a problem, you're getting penalized and your ceiling in that problem becomes an 8. And then you'd have to try and get 6 out of 8 points, which is more work. So pay attention to the units. When in doubt, include units. Okay? So that's up there. You're going to exercise number 1, please. All right, so it's the same problem with a different geometric shape, and you'd be here. The volume equals side cubed. So the derivative of the volume with respect to the side power rule. Here are the two inputs you were given. You want an input for 1, an input for 5. Here are the outputs. But the change in volume with respect to the length of the side would be in inches cubed per inch, because the side is changing by inches and the volume is a cubic measure. So you would be expected to say the derivative when the side is 1 is 3 inches cubed per inch. That's the instantaneous change then. The derivative when the input's 5 would be 75 inches cubed per inch. Okay? So in the textbook, there's a difference. Ready? You got right here. See this instantaneous velocity after average velocity? Average velocity is the slope of the secant line. We will show you a picture for that. Instantaneous velocity goes with the slope of the tangent line. And down here, all this is delta t is replacing the h. So we think of h as being a horizontal change. And here they're saying in terms of motion, it's time. So delta t is your h. It's the same thing you saw. So if we go over here, the average velocity of this blue curve from P to Q is the slope of that black line that connects P and Q. The instantaneous change, the velocity at P, is the slope of the tangent line. That's the difference. Average change versus instantaneous change. And you're going to get these questions and you have to read them to detail. You have to read them carefully because that's the number one mistake people make. They make an assumption. This is looking for average. This is looking for, I'm using derivative all the time. They don't want average. And if they do, then the instantaneous change would probably be choice A. And if you're not reading the problem carefully, and the instantaneous change is choice A, you won't even read the other choices. Read to detail. Speed. Now, if you're in physics, it's not a big deal. Speed is the speed is the absolute value of velocity. So what does that mean? Well, if you're in your parents' car and you're backing down the driveway, the car is in reverse. But when you put your foot on the gas, the speedometer is still going into positive units. Hopefully you're not looking at the speedometer when you're going in reverse, but take my word for it, it's going in positive units. So speed is the absolute value. It doesn't matter what direction you're going. Acceleration is the derivative of velocity. So it's the second derivative of position. And then they give you these constants. You've seen this multiple times. Ready? You're used to seeing a negative here. Negative 1/2 times the force in feet per second squared of gravity and the force per meter squared of gravity. There's no negative here because they're saying they're measuring how far something fell. The negative is going to help us find out how far it is off the ground. So I want to back up to example 3. In example 3, we have this picture. This picture is a picture of the derivative. We have these motion detectors. I think we have them in the building on the first floor. This is a velocity graph. And they're asking you to interpret this. Okay, so here's the picture. So what do you notice? Well, the tick marks are worth 4 horizontally. 4, 8, 12, and halfway between 12 and 16. So the first 14 seconds, someone's going forward. The next 4, 8, 12 seconds, they're going backwards. The next 2, 6 seconds, they are standing still, and then they begin to go forward again. So the questions are, describe her motion. Yes. When is the speed at a maximum? The speed, ready? If you wanted the speed graph, you would just take this part of the graph that's below the x-axis and reflect it over the x-axis. But the speed's maximized when this velocity graph has the greatest distance from the axis. So this, when she's going backwards at her greatest speed, because this is farther from the x-axis than this is. You just count it. 2, 4, 5, 2, 4, 5, 6, 7. Okay? So in your book, number 9, there's another picture, and you're going to answer the questions for number 9, which is just this same thing with a different graph. Okay? Okay, so here's the picture. And I'm saying this. Now, instead of the ETR method, going A, B, C, D, the bullet points, I just summarized all the information that I could take out of this, and we'll go back and answer it. So when is it going forward? Well, look at the picture, and from 0 to 1 and 5 to 7, the graph is above the x-axis, so it's going forward. Between 1 and 5, it's below the x-axis, so it's going backwards. When is it speeding up? It's speeding up between 1 and 2 seconds and between 5 and 6 seconds, because it's moving away from the x-axis. Now, if you haven't had physics, part B's harder for you, but you can see it. I mean, when is it slowing down? When it's going towards the x-axis. Y = 0 is the x-axis. So between 0 and 1, it's going towards the value of 0. Between 3 and 5 and between 6 and 7, it's slowing down. When is the acceleration? Positive. The acceleration is the derivative of that picture. That's the velocity curve. So I'm looking for this to have a positive slope. Between 3 and 6, it's negative. From 0 to 2 and 6 to 7, negative slope. And it equals 0 between 2 and 3 and 7 and 9. The maximum velocity. Now this is interesting, ready? It happens at the end point. At 0, that's as far from the x-axis as it is between 2 and 3. So don't forget the endpoints. And then it's still between 7 and 9 seconds. Okay? Well, problem 10, like, I'm confused about that. Yeah, 10 you could do, except you want to wait because 10 involves the beta lesson. But then there's 11. It's another picture. And you have your book, the PDF that's on Canvas, has the answers. It's actually the teacher's edition. You know that. Example 4. So example 4, ready? Here are the constants we talked about. Modeling vertical motion. So you saw this problem multiple times in Algebra 2. And what have you got? Here is position. S equals 160t plus a negative 16t squared. This is negative now because you want the position, not how far it fell, but how far it is off the ground after so many seconds. So what happened was when you were in Algebra 2, here's the graph you came up with in function mode. Except this graph confused people that don't get to calculus because they looked at this as this was the path of the particle. It's not. See, the independent axis is time, not horizontal distance. The path is straight up and straight down. And that's what we're going to be able to start dealing with on Monday. But for this part, ready? This is how high it is after this many seconds. The derivative is this black line segment. So what's that telling you? The derivative is positive here between 0 and 5 seconds, and the blue graph is going up. After 5 seconds, the blue graph is going down, and the derivative is negative. So this is the connection you have to make. I don't know what that is. If I take what that was, what's in the book for example number 4, and I rewrite it in standard form, I would have S equals negative 16 t squared plus 160 t. The derivative of S with respect to t would be negative 32t plus 160. And there's actually a plus 0 up here, which is initial height. So if I put a 0 in here, in this line, negative 32 times 0 is 0, you would just get 160. And that's why the coefficient up here is the initial velocity. Ready? The position is, this is gravity. Negative 1/2 times the force of gravity in feet per second squared. If it's feet, you have 32. So that's where the negative 16 is. We don't need to write the negative 1/2 times 32. The initial velocity is the coefficient of t to the first. And here's the initial height. It's the initial height because if you put in 0 for t, cover-up method, you would just get whatever the initial height is. And if you do cover up to the derivative, you put 0 in there, cover up method, you would just get this coefficient of t. All right? So what's happened is you used this before you understood why this coefficient was the initial velocity. Well, you couldn't understand it until you could differentiate the position graph. So you're there now. What we're going to do on Monday is go to vertical and horizontal motion. We're going to leave function mode on your calculator and go to parametric mode. So we're going to stop.